Thank you. Okay, so let's continue on looking at several things. So we talked about what is organic chemistry, we talked about the theory of vitalism, and we looked at formulas. Today we're going to cover a few things. One is constitutional isomers. We'll also look at indices of hydrogen deficiency, and we call these IHD. We will look at valence, which is something you have met already in Gen Chem. But we're also going to look, and we spend some more of the time, and start this one first, looking at the structural theory. And there are several parts of organic chemistry, several parts of this course that I will tell you this is really important for you to grasp from this series. The structural theory is one of those things. In fact, most of the items on the board are some of those things you really want to grasp and get a good working knowledge of in order to move forward in organic chemistry and those courses that follow it, particularly biochemistry, for example. So let's talk about the structural theory. So the structural theory really is, at its heart, a series of very simple rules that govern our ability to draw reasonable structures for organic compounds. So for example, suppose I tell you I have a compound of formula CH4. So let's say the molecular formula for a compound is CH4. And I ask you, draw that for me. Draw the structure of CH4. So this is molecular formula, which also happens to be the empirical formula. They're the same thing in this case. And what I want to get is a structural formula for CH4. In other words, how are the atoms connected to each other? That's what I mean by the structure. Who is connected to who? Well, I could say, why don't I just draw CHHH? What about that for a structural formula? Or maybe I can say, what if it's not CHHH, and then maybe another H? Now, why did I do that? Well, it turns out both of those are rubbish, and we'll see why in a second. But the structural formula is a series of rules that allow us to make good judgments about what kinds of structures we can draw. And so I'm going to leave this on the board for a second to show why they disobey the structural theory. And I'm going to go ahead and write down one of the basic precepts of the structural theory. So the structural theory essentially holds that all atoms in organic compounds have a fixed valence, right? And that the valence is determined by their position in the periodic table of elements. In other words, and you remember this from Gen Chem, if you are in group, so if you're in group 1, so you're an alkaline metal, then you are monovalent. So you form cations of charge 1+, so sodium plus, lithium plus, and so on. If you're in group 2, then you are divalent, for example, beryllium 2+, calcium 2+, and so on. Now, if you're in group 3, and group 3 is interesting because at group 3, you have elements that are both metals, and then you have metalloids and you have metals. And then in group 4, you have elements that are non-metals, and you graduate down to metalloids and then to metals as well. But for us in organic chemistry, we are typically concerned with elements that are either in groups. We see elements that are in groups 4, groups 5, group 6, group 7. And sometimes they're written if you look at the classic way of writing it, Roman numerals, groups 4, 5, 6, and 7. And then group 8 would be the noble gases. So we're looking here then at the carbon group, right? This is carbon, silicon, and so on. And then this is nitrogen and phosphorus. This is oxygen and sulfur. This is fluorine, chlorine, and so on, right? So these are the first two elements of those groups. So if the element is in group 4, it is tetravalent. So there's a valence of 4. And if you remember, we pointed out last time that that was one of those essential features of carbon that made it unique, that made it valid for it to be the center of an entire sub-discipline in chemistry. Right? And carbon was tetravalent. If you recall, that led to carbon forming a large number of compounds and a large variety and complexity, a real wealth of organic compounds. So if you're in group 4, you will be tetravalent, and you will always be tetravalent. That's what the first precept is. That all atoms of organic compounds will have a fixed valence. They will always have a valence. That valence is determined by their position in the periodic table. So if I'm in group 4, I am always tetravalent. If I'm in group 5, 6, and 7, my valence will essentially be 8 minus the group number. I suppose I can say the same thing for group 4. So their valences for all of these, their valence, in other words, the number of bonds that they will form, will be equal to 8 minus the group number. 8 minus the group number. So if I'm in group 4, my valence is 8 minus 4, which is 4. If I'm in group 5, my valence is 8 minus 5, which is 3. So these are trivalent. If I'm in group 6, my valence is 8 minus 6, which is 2. These are divalent. If I'm in group 7, my valence is 8 minus 7, which is 1. These are monovalent. Okay? So the halogens are monovalent, 8 minus 7. The chalcogens are divalent, 8 minus 6. The pnictogens are trivalent, 8 minus 5. And the group 4 elements, the carbon group, they have a valence of 4. 8 minus 4. And by the way, the 8 is not a magic number. The 8 comes from the octet group. Right? It basically is asking the question, so the element wants to have a noble gas configuration. Okay? The element wants to have a noble gas configuration. If I'm in group 4, I already have 4 valence electrons. How many more do I need? And the answer is 4. Which is why my valence, the number of bonds I will form, will be 4. If I'm in group 5, I already have 5 valence electrons. How many more do I need to have an octet? The answer is 3. So I will invest in 3 bonds, because each bond I invest in, the atom brings in an electron. Right? So if I'm in group 5, like nitrogen, so 1, 2, 3, 4, 5, those are the valence electrons in nitrogen. Nitrogen wants to get a noble gas configuration. So what will nitrogen do? It will bond with an H having 1 electron, an H with 1 electron, and an H with 1 electron, for example. And that way, by forming 3 bonds, it now acquires a total of 2, 4, 6, 8 electrons. So this 8 is from the octet group. Similarly, O is in group 6. So O will have 1, 2, 3, 4, 5, 6. It already has 6 valence electrons. It needs to get 2 more for an octet. So it will go ahead and form 2 bonds. Let's say the H's as well. So H will bring in 1 electron, H will bring in 1 electron, and now the O's are sharing 2, 4, 6, 8, and that's an octet. So the 8 is not a magic number. It comes out of the octet group. Right? These elements, having a noble gas configuration makes them completely stable, and that's the reason they bond. So the first rule of the structural theory is that all atoms carbon, hydrogen, oxygen, nitrogen, sulfur, chlorine, blah, 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 will have a fixed valence, and that valence is determined by the position of the element in the periodic table. The other rule, the other tenet, if you will, of the structural theory is that elements that are multivalent, so multivalent elements, in other words, those that have a valence greater than 1, right? So these are, so not the halogens and not hydrogen, but these are the chalcogens, oxygen, sulfur, so on. The pnictogens, nitrogen, phosphorus, and then the group 4 elements. All multivalent elements, or multivalent elements, can form multiple bonds with other multivalent elements. And that makes sense. If I have a valence greater than 1, let's say carbon is tetravalent, and carbon is bonding with O. Well, carbon can do this, so it can form a multiple bond to oxygen, or maybe it can do this. So if I look at this compound, the H is monovalent and can only form 1 bond. The O is divalent, and it can express its divalence in 2 ways. Either it can form 2 single bonds, we talked about this in the last lecture, or it can form a double bond, and that's perfectly legal. Carbon is tetravalent. It can express its tetravalence in 4 different ways. And if you remember in the menu, one of the options was a double bond and 2 singles. If you recall from the last lecture, I can express tetravalence either with 4 singles, a double and 2 singles, 2 doubles, or a triple and a single. There are 4 ways that I can express my tetravalence. So, something like this compound is called carbonic acid, by the way. It's found in bubbly drinks like sodas and beers and so on. This shows the ability of carbon to form its 4 bonds, O to form its 2 bonds in 2 different ways, H to form 1 bond. But if I'm multivalent, I have the ability to form a multiple bond. In this case, this is called a double bond. I can form a multiple bond with another multivalent element. I could, or I could not. Okay? So let's go back to this structure. Let's say again, the question was, draw the structure of CH4. CH4 is called methane. Methane is it's also called natural gas. It's also called natural gas, or sometimes called marsh damp. So that's an old term for it. Natural gas is the gas that's pumped into your homes. So if you have a gas stove at home and you're cooking, the gas that you're burning to cook your food is methane. And it's also the degradation product of anaerobic degradation. So in swampy land, where there's not a lot of oxygen in the water, there are bacteria that are called anaerobic bacteria that break down organic materials, and one of the products is methane. So it's called marsh damp. So if I want to draw a reasonable structure for methane, so it's got 1 carbon and 4 H's, well, what about this structure? Would this be an acceptable structure, knowing what we know about the structural theory? Well, let's see. Here, carbon is monovalent. It's forming 1 bond. So this can't be right. Because I know that all the atoms must have a fixed valence, but it's determined by where the element is in the periodic table. The group number of the element determines its valence. If I'm in group 4, my valence is 8 minus 4. So carbon must be tetravalent. It's not here. It's monovalent. This structure can't be correct. And that's enough to disqualify it. But if I move further, these two H's are divalent. Well, that's not legal. H, as you know, in group 1 is monovalent. H cannot form two bonds. So this is out, that's out, that's out, and really only one is needed to disqualify it. So this is not a reasonable structure. The only part of it that's reasonable is this one, but the rest of it disqualifies it. So I know this cannot be a reasonable structure for methane. What about this one? Well, this is probably worse. Because again, this carbon is divalent, two bonds. That's not allowed. Carbon has to be tetravalent. This H is divalent. That's not allowed. So is this one. That one is trivalent. This one is monovalent. So here I have three flavors of H. One is monovalent. That's allowed. Two are divalent. Not allowed. One is trivalent. Right? So again, this structure is not reasonable because it does not obey the structural theory. So the structural theory is a series of guardrails that keep you on track in terms of what structures are reasonable. And they're just two very basic parts to it. One, all atoms in organic compounds have a fixed valence. How do I know what the valence is? I look at the periodic table. The group number defines the valence. If I'm in groups 4 to 8, well, 8 is a noble gases, so they don't really bond. If I'm in groups 4 to 7, my valence is 8, octet 8, minus the group number. Now, if I'm in groups 1 to 3, my valence is the group number, because those are the number of electrons I will lose to get a noble gas configuration. So, how do I draw then the structure of methane? How can I draw that? Well, I know the only thing that H can do is that H is monovalent. So if I have one carbon and 4 hydrogens, and I look at the options, right? I look at the options that are available. Well, clearly, I can't use this one. Because sticking an H here is not possible because H can't form a triple bond. Right? I can put an H here, that will be okay, but I can't use that sign, so this is out. Can't use the H here for exactly the same reason. H can't be divalent. Can't do this is completely out. The only option that connects a carbon in one of its iterations, its valence iterations, and a monovalent H is this one. So I can stick an H, an H, an H, an H, and that is a reasonable structural formula of methane. And it turns out to be the correct one. So I can use a structural theory as a guide to draw reasonable structures for organic compounds. That is one of the most important features you will take out of this class, to be able to draw reasonable structures that represent organic molecules. And as we saw in the last lecture, it's very important for us to be able to draw reasonable structural formulas because we use the structural formulas to gather data. You recall I had drawn two compounds of formula C2860. One had this structure, and the other had this structure. You will notice that both of these structures are obedient to the structural theory. Carbon having 4 bonds, 1, 2, 3, 4. O having 2 bonds, 1, 2. H forming 1 bond. Right? Tetravalence of carbon, 1, 2, 3, 4, or 1, 2, 3, 4. O showing divalence, 1, 2. H showing monovalence. But the structural theory allows me to make judgments about the compound. And I said, based upon the structure, that compound is going to be a gas room temperature. It will burn. It will also be insoluble in water. This compound is a liquid room temperature. It will burn. It will be miscible in water. It will dissolve infinitely. I know that based upon the structural formula, right? And the way the molecule is connected, the way the atoms are connected. So getting the right structural formula is absolutely critical. Okay. We've talked about the structural theory, and the ability to draw reusable structures. We talked about valence, right? Valence is determined by the position of the element in the periodic table. Let me talk about that a little bit more. I just want to make sure we understand how this sort of works. And I gave two examples earlier, but so I'll just give one more example. If I look at carbon, carbon, and I'll draw it this way in terms of its the number of valence electrons that carbon has in its Lewis structure. That element has 4 valence electrons. To acquire a noble gas configuration, it means it needs to have 8. So what carbon will do is try to solicit 4 additional electrons. And that can happen in a couple of ways, right? One easy way is to bond with 4 atoms, each bringing 1 electron. So I can bond with an H having 1, an H having 1, an H having 1, an H having 1. So if I do that, what I'll get is C, H, 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 which is my CH4. So instead of drawing a Lewis structure, where I show the valence electrons as lone pairs, right? I could draw, let's say, a dot structure. I can draw what's called a line structure, where I show the electron pairs by lines. Okay, they're equivalent. But there are other ways that carbon could do this, right? So if I go back to this compound, right, which we call carbonic acid, how is carbon managing to do this, right? So this is a more involved question, and what I'll do is I'll break up the elements into their individual Lewis structures. So imagine the H with 1 electron, and this O is in group 6, so it has 6 valence electrons. The carbon is in group 4, so it has 4 valence electrons. The O is in group 6, so it has 6 valence electrons. And then there's another O with 6 valence electrons. And then another H with 1 valence electron. And I've taken the liberty of moving the electrons around. It's the same numbers, but I've moved them around to allow my bonds to form in the way I've drawn it. So here is the H donating 1 electron to link with the O to form this bond. Here is the O with 1 electron linking with 1 of the valence electrons on the carbon to form that bond. The carbon has 4 valence electrons in all. I've used 1. I'm going to use 2 more to bond with 2 of the electrons on the O to form a double bond, because each covalent bond has 2 electrons in it. There are 4 electrons here that corresponds to a double bond. 2 electrons per bond. 2 electrons per bond. If I've got 4 electrons, that's 2 bonds. That's a double bond. I'm going to form a single bond here with 1 electron from the carbon and 1 from the O. I'm going to form a single bond here with 1 electron from the O and 1 from the H. And here's the point. Everybody has an octet. Everybody has a noble gas configuration. H has a duplet, which for H and elements in the first period defines a noble gas configuration. Not all noble gas configurations are octets. Strictly speaking, they're octets only for the second row elements. Right? So duplet for the H, duplet for the H, octet for the O, 2, 4, 6, 8. Octet for the O, 2, 4, 6, 8. Octet for the carbon, 2, 4, 6, 8. Octet for the O, 2, 4, 6, 8. So everybody has a noble gas configuration, and I've satisfied everybody's valence in the structure. Just a really quick point, since I mentioned it, and this is something you have met in Gen Chem 1. So I mentioned that the octet rule really only strictly applies to elements in the second period. They do not apply to elements in the first, they can't possibly. And they don't really apply to elements in the third period, although we say that kind of tongue-in-cheek. Let me just explain why that is the case. If you recall, if you are in the first period, so if you are a first row element in energy level number 1, if you're in energy level number 1, you only have access to the 1s orbital. The 1s orbital can hold a maximum of 2 electrons. That's it. In other words, there are only 2 seats on the bus if you're in the first period. Which means for you, a filled shell, a noble gas configuration, is defined by a duplet. If you're in the second period, you have access to the 2s and the 2p's. Well, there's only a single 2s orbital, but there are 3 2p orbitals. Each orbital, regardless of its type, can hold 2 electrons. So in theory, the second period can hold a maximum, the orbitals in the second period could hold a maximum of 8 electrons. This is where the octet comes from. Right? So octet for second row elements strictly applies to second row. Duplet for first row elements. Now, if I'm in the third period, technically I have 3s, 3p, and 3d. There's a single 3s, there are 3 3p's, and there are 5 3d's. So technically the rule that elements in the third period have to obey is the 18th rule. Right? There are 18 seats on the bus if you are in the third row, and then more in the fourth and more in the fifth and so on. Now there is stability to be had if you only fill the 3s and the 3p. So the octet for third row elements provides stability, but they are not locked in to an octet. If you're in the second period, yeah, you're locked into an octet. And since organic chemistry is a chemistry of carbon, we're pretty much focused on the octet rule for organic chemistry, because carbon is a second row element. These are the governing precepts for carbon. Okay, so we've talked about structural theory, we talked about valence. Let's talk a little bit about, let's do constitutional isomers. And it turns out we've actually talked about that already. So isomers are different compounds with the same molecular formula. Isomers are different compounds with the same molecular formula. And if you remember, we looked at C2H6 a little while ago. C2H6O, and we ended up with CH3O, CH3, and we ended up with CH3CH2, OH. These two compounds are said to be isomers of each other. So isomers are different compounds. This you can drink without dying. Well, you know, this is the alcohol found in beer and rum and wine and so on. So when you can drink a glass of wine, 2 glasses, maybe 3, but if you drink 2 or 3 bottles of wine in a short measure, that is toxic. Right? I mean, you can die from alcohol poisoning. But you drink well, it's hard to drink that, you have to breathe it in. But you breathe in, a half a liter of that thing, the gas, and you're going to be blind temporarily or permanently, or you're going to be dead. So this is far more toxic than that. This is a colorless gas, this is a colorless liquid. This dissolves in water, this one does not. So they're very different compounds. So these are different compounds, but they share the same molecular formula. So these are called isomers. Now, it turns out there are lots of ways in which isomerism, the phenomenon in which isomers exist, it turns out there are lots of different ways in which isomerism can exist. One of them, the one we're going to talk about today, is constitutional. In other words, it depends upon the constitution of the molecule. And constitution is another word for connectivity. In other words, we're looking at who is connected to whom. So in this compound, I have H attached. So in this compound, I have H attached to O. That's not present here. In this compound, I have C attached to C. That's not present here. In this compound, if I look at the skeleton, I've got COC. Here I've got CCO. So the connectivities are very different. So we say these types of isomers are constitutional isomers. So constitutional isomers are isomers, different compounds in the same molecular formula, that differ in terms of connectivity or constitution. Okay, and we will see lots of different kinds of isomers as the course develops. But I'm also going to show us how to do more examples of constitutional isomers. And again, we will use a structural theory to help guide us, right? So, and I did this sort of automatically. I'm obedient to the fact that carbon must be tetravalent, 1, 2, 3, 4, O divalent, 1, 2, H monovalent, right? So, and so on and so on and so on. Let's talk about the indices of hydrogen deficiency. So let's say I ask you to draw 2 isomers. Let's say I ask you to draw 3 isomers of formula C2H4, well, let's say C3H6O. So my question to you is draw 3 isomers, 3 constitutional isomers. Draw 3 constitutional isomers of formula C3H6O. Okay? So I can decide, well, hey, let's do that the way we started. Why don't I have a CCCO skeleton? I could try that. And then maybe that would be different from a CCOC skeleton. I could do that. And let's try to go ahead and stick some atoms on. And in fact, why don't we do a third one? Because I asked for 3. Why don't we do a CCCO skeleton? Okay, let's do that. So these are 3 different skeletons. So what I'm going to try to do now is to populate each atom with H's, being obedient to the structural theory which insists on every element having a prescribed valence. Okay, so let's go ahead, and I've got 6 H's. Carbon is tetravalent, so I'm going to go 1, 2, 3, 1, 2, 1, so I've got 1, 2, 3, 4, 5, 6, and we're in trouble. Because I don't have enough H's now to complete the valence of this carbon or the O. So there's something funny here. If I try it here, 1, 2, 3, 4, 5, well, I'm not going to put an H on this O because the valence is satisfied for the O. But now if I put an H here, we've got a problem, right? Because there's something wrong with this carbon and that O. There are not enough H's in the formula. So there's something funny with this one. This carbon only has divalence. And according to the structural theory, it must be tetravalent. Maybe this one will be better. We try 1, 2, 3, 4, 5, and good grief, we're in trouble again. And I could have put the extra H in this carbon. It would still been in trouble, and then the O would have been out. So what the hey, right? I mean, we're trying to obey the structural theory, but something is wrong with the structural formulas because the carbons, some of the elements do not have the correct valencies. So what's the problem? And the problem is that when we look at these compounds, when we look at the formulas of the compounds, before we start to draw anything, what we have to determine is what is the index of hydrogen deficiency in the compound. So for example, we're going to go ahead and do the following. I'll come back to this example in a second. So my point is, you never want to just jump in and start drawing. Once you have a formula, don't just jump in and start drawing stuff. Okay? There is something to work out first before you do that. And the way we do this is to take a fairly simple example. So let's take this compound. So we take a very simple hydrocarbon. We take a C4 hydrocarbon. And the formula of this compound is C4H10. So this is C4H10. Right? 1, 2, 3, 4, H3, 5, 7, 10. Okay. I'm going to ask the question, what would happen to my formula if I stuck a double bond between a pair of carbons? I don't care which pair. Let's take a double bond between carbon 1 and 2. So I'm going to redraw my skeleton, but now I'm going to put a double bond between carbon 1 and 2. And for that matter, what if it was carbon 2 and 3? It doesn't really matter. Now, obviously, between these two carbons and these two carbons is exactly the same. Right? When I read across the molecule, it's exactly the same. What would I get? Well, now that I have a double bond, I can only put 2 H's on this carbon to complete the valence. This carbon is a double and a single, that's 3 bonds, I can only put 1. 2 bonds, I can put 2 H's, and then 3 H's. Right? Carbon is forming 1 bond here. According to structural theory, I can form 3 more bonds, or I should form 3 more bonds, I must form 3 more bonds. This carbon is forming 1, 2, 3 bonds. We form 1 more, 1 more, 1, 2, 3. And if I work out the formula now, it is C1, 2, 3, 4, we'll change that, H2, 3, 5, 8. C4, H8. What about this one? C4, H3, 4, 5, 8. So really, I can ask you, these two are structural isomers of each other, right? They differ in connectivity. In this case, I have a carbon doubly bound to another carbon between 1 and 2. That's a different arrangement than here. So these are structural isomers of each other. But more to the point, the introduction of a double bond anywhere in the compound causes me to lose a pair of H's. Because when I had no double bonds, when I had the acyclic, that's a word I haven't used before, this is an acyclic species. In other words, it's not a ring. So if I have an acyclic compound that has only single bonds, right? This was my first example. Let's say it had 4 carbons. I'm going to have 10 H's. But once I put a double bond in, all of a sudden, I've lost 2 H's. Okay? What would have happened if I made a ring? If I made it cyclic? So, I'm going to go ahead and zip together carbons 1 and 4. 1, 2, 3, 4. So I'm going to go 1, 2, 3, 4, and zip them together. If I complete the valences on the carbons, well, that formula is C1, 2, 3, 4, H2, 4, 6, 8. That's also C4H8. And by the way, it doesn't matter if the ring is a 4-membered ring, or I could do a 3-membered ring and have a 1-carbon appendage. It doesn't matter whether it's on this carbon, that carbon, that carbon, they're all the same. If I do that, and I complete the valences with H's, 1, 2, 3, on this carbon I'll have 1, so I have 1, 2, 3, 4 bonds, 1, 2, so I'll have 1, 2, 3, 4, 1, 2, so I'll have 1, 2, 3, 4. What's my formula now? C1, 2, 3, 4, good, H3, 4, 6, 8. So the introduction of either a double bond or a ring, doesn't matter what the size of the ring is, causes me to lose a pair of hydrogens. And you notice the currency is always a pair of H's. I'll never lose one H or half an H, which is absurd. I'll never lose 3 H's or 7 H's. I'll always lose them, I'll always miss them in pairs. So a pair of H represents an index of hydrogen deficiency of 1. So if I say, if you give me a formula of C4H8, and you tell me draw an isomer of that, the first thing I'm going to do is say, well fine, what is my index of hydrogen deficiency? I'm going to compare C4H8 to the corresponding formula, which is CnH2n plus 2. CnH2n plus 2 is the generic formula for a class of compounds which serve as my reference. They're called alkanes. Let's explore this for a second. What are my alkanes? Well, my alkanes represent the simplest class of organic compounds. They are hydrogen, they are hydrocarbons because they have only H and C. And you can imagine that when N is 1, when N is 1, my formula is C1, you never write the 1. H2 times 1 is 2, plus 2 is 4. That's methane. That's the natural gas. That's the marsh gas. That's what's pumped into houses. When N is 2, our formula is C2H6. C2H2 times 2 is 4, and 2 is 6. When N is 3, C3H8. When N is 4, C4H10. When N is 5, C5H12. You will notice, by the way, that each consecutive member of this family, of this class of organic compounds, differs from its predecessor by CH2. Right? I will gain an H, I gain a carbon and 2 H's between members as I increase my number of carbons. And that's how we know that different compounds are members of the same family. The successive members are enriched by CH2. So, the presence of either, so what I would do, if you gave me this formula, C4H8, and say draw isomers of it, the first thing I would do is say, fine, I want to get the alkane with the same number of carbons. I want to get the formula of the corresponding alkane. The alkane with the same number of carbons. If I have 4 carbons, that's C4, H2 times 4 is 8, and 2 is 10, that is C4H10. I'm going to subtract. The carbons cancel. I'm left with 2 H's. 2 H's correspond to one pair of H's And this 1 is my index of hydrogen deficiency. And an index of hydrogen deficiency of 1 could either mean a ring, regardless of the size of the ring, or a double bond, regardless of which atoms the double bond is between. Right? So in a case of this compound, it could be between carbons 1 and 2, or 2 and 3. And then when we get to compounds having heteroatoms that are multivalent, the double bond could be between carbon and carbon, or carbon and O, or N and O, or carbon and nitrogen, or nitrogen and sulfur. It doesn't matter. As long as there's a double bond, it corresponds to an HDI of 1. Okay, well, what if I had put in a triple bond, right? What if I took my C4 species and I put in instead a triple bond? What would happen then? Well, let's take a triple bond in. We'll do the same thing we did the first time. We have the C skeleton. Let's put a triple bond between carbons 1 and 2, and let's complete the valences of the carbons with H's. So I can put an H on this carbon, but none on that, because it's already tetravalent, 1, 2, 3, 4. We haven't messed with those. What's my formula now? Any guesses? Well, it's C4, H, 1, 2, 3, 6. So now I'm 2 H's short. I'm 2 more H's short when I introduce a triple bond. So I can already tell that C4H6 corresponds to a deficiency, a hydrogen deficiency of 4 H's. 4 H's is 2 pairs of H's. So my index of hydrogen deficiency is 2. The triple bond could either be between carbon 1 and 2. It could very well be between carbon 2 and 3, in which case I'll have 3 H's here. None here, because I'm already tetravalent, 1, 2, 3, 4. Structural theory. None here, 1, 2, 3, 4. Here, I only have 1 bond. I've got to have 4, so I'm going to go 1, 2, 3. So 1, 2, 3, 4, and we're good. What's my formula? C4H6. But I know that, because we just learned, an HDI, or an IHD, and by the way, and I will use those terms interchangeably. I will either say the IHD, the index of hydrogen deficiency. I can also say the HDI, the hydrogen deficiency index. So either the index of hydrogen deficiency or the hydrogen deficiency index. They mean the same thing. But we learned earlier, just 5 minutes ago, that an HDI or an IHD of 1 could mean a double bond or a ring. So if I have an HDI of 2, which can mean a triple bond, well, that's good. But it can also mean 2 double bonds, or maybe 2 rings, or maybe a double bond and a ring. So let's explore those. I'm going to take my C, so I could do it that way. So that's 4 carbons with 2 double bonds. Or heck, I can make the double bonds alternate. 1, 2, 3, 4. Let's complete those. Putting in bonds. 1, 2. That's all I'm allowed. Be tetravalent. Can't put any here. That's already tetravalent. I can only put 1 here because I've got 1, 2, 3 bonds already. Structural theory. And then this carbon has 1 bond, so 2, 3, 4. And what's my formula? C1, 2, 3, 4, H2, 3, 6. What if I put the double bonds this way, so they alternate? Double, single, double. Well, 1, 2, 3, 4, 5, 6. So C4H6 could either be a triple bond, different options, 2 double bonds, different options. It could be a ring, right, with a double bond in it. That gives me 1, 2, 3, 4, 5, 6. Okay? And it doesn't matter where I put the double bond, whether it's here, 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 or here, it's the same thing. It could have been a 3-membered ring with a 1 carbon appendage, and the double bond could either be exocyclic, in other words, it could be out of the ring, or the double bond could be endocyclic. This is endocyclic. In other words, it's a double bond that is inside the ring. And by the way, it could be here, or for that matter, it could be here. Because these are different. Because the position relative to this carbon is different. Now, let's just complete the valences here. So 1, 2, 3, 4, none here, 5, 6. 1, 2, 3, 1, 2, 3, 4, so none here. 4, 5, 6. 1, 2, 3, 4, 5, 6. They're all C4H6. They're all constitutional isomers. So with 2 HDIs, I can have a triple bond, 2 double bonds, a ring and a double bond, or I could have 2 rings. So why don't we try something like this? Let's do a C4 system with 2 rings, and pretty much the only way we can get that done is that 1 ring, 2 rings. Complete the valences. 1, 2, 3, 4, 5, 6. Now, we talked about the complexity of organic chemistry yesterday and why carbon was so special. All I have is C4H6, right? Look at how many options I have. And by the way, we have not exhausted them yet. So carbon's ability to form, to be tetravalent, and to express that tetravalence in multiple ways, its ability to form chains and rings leads to a plethora of organic compounds. And there was just simply no way to study all of it under just the umbrella of chemistry. You had to separate organics out. It was just too much. So what this leads us to then is a very interesting discussion, which is centered on the importance of working out indices of hydrogen deficiency. And what I'm going to do then is construct a table, which we've already seen the elements of, for how to handle indices of hydrogen deficiency. So if the IHD, right, and I'm going to say double bond, ring, triple bond, there is another one that we have not met, which is the benzene. And the benzene ring is a unit unto itself, because that has 4 HDIs. Okay? So if a compound has 0 HDIs, what of these structural features am I allowed? Right? So if you ask me to draw a compound formula C4H10, do I have to look out for a potential double bond, a potential ring, a potential triple bond? Let's see. C4H10, I will compare that formula to that of the corresponding alkane. The alkane, CnH2n plus 2, that has the same number of carbons. So for 4 carbons, this will be C4H, 4 times 2 is 8 plus 2 is 10, which means I have no H's. I have, in a system like this, I have no rings, no double bonds, no triple bonds. So if I have 0 HDIs, or IHDs, I have no double bonds, no rings, no triple bonds, no benzene. What if I have 1 HDI? What can I have? Well, we saw that earlier. I can have 1 double bond. But if I did, I couldn't have anything else. Or I could have 1 ring. But if I did, I couldn't have anything else. And if you remember, I'm just going to remind you of that very quickly. So for C4H8, we could have gotten this structure. I won't draw them all, but I'll just draw a couple. We've got this structure, or for example, this structure. So I could have had either a ring, or I could have had a double bond. But if I have the double bond or the ring, I can't have anything else. What if I had 2 HDIs? What can I have? Well, we saw it here. Either I could have a triple bond, so I can have a triple bond, but then I'm not allowed anything else. I could have 2 double bonds, right? I could have 2 double bonds, but if I do, I'm not allowed anything else. I could have 1 double bond and 1 ring, or I could have 2 rings. Okay? Now, I'm going to rewrite this in a more systematic way. This is perfectly fine. But I like to be systematic. I did these based on what I had on the board, but I prefer them to be systematic, so I will do it this way. I will say, if I have 2 HDIs, I'm going to go down the list. I can have 2 double bonds, and then I'm exhausted. I can have 1 double bond and 1 ring, and then nothing else. I could have no double bonds and then 2 rings. So this is systematic, right? I start with 2, then 1, then 0. 0, then 1, then 2. I'll have nothing else. Or I could have none of these, no double bonds, no rings, 1 triple bond, but then I'm allowed nothing else. And as it turns out then, and you could see how this is going to go, and as an exercise, what I'd like you to do for me, and we'll do this in class on Thursday, is work this table down for 3 HDIs and 4 HDIs. Right? What options am I allowed with 3 HDIs and 4 HDIs? Now, I want to make a point here And the point is, this is not anything that is, maybe I should do 3. Okay, let me do 3 HDIs. So if I had, so again, it would be, so IHD, double bond, ring, triple bond, benzene. If I have 3, I can have 3 of these, none, none, none. 2, 1, none, none. 1,